Evening, sir.
Yeah, good evening. Good evening.
Hi Jattana ji, good evening.
Yeah, good evening. Good evening, Ji. How are you?
I'm doing fine, sir. How are you?
I'm good, sir. Nice to see you on screen
Yes.
after 6, 7 months.
Yes. It's been a long time.
Yeah,
So you are in Chandigarh only, right?
Chandigarh.
Yes.
Oh, I'm Chandigarh.
Recently I was in Chandigarh for couple of hours.
Oh, couple of hours. Okay, you could have told me. We could have met.
No, we were actually going to Manali
Busy.
for a trek.
Okay.
So we just came to Chandigarh and took a cab from there actually.
Okay.
It's not even couple of hours. It's probably a few minutes.
Yeah, you just
Directly from the airport.
passed
Yeah.
through the city. Yeah, Manali is good.
Yes, it's a nice place. We did some trekking there.
Okay, good. Yeah, one can spend 3, 4 days in Manali. Nearby, there are
Yes,
good trekking sites.
yes, quite a few trekking sites. Yeah. So people still joining?
Yes, sir.
Is it possible to see how many joined so far?
One. So you see the below the numbers? The right side on your right, participants.
I cannot see it. No, I don't see that on my screen. Yeah, I don't find any button that shows me the. Okay, I can see. Now, if I click on the chart, it tells me 117. Okay, 117. Okay.
That's just increasing one by one. People are just started joining, I guess.
Okay. So we'll give it another 2-3 minutes and get started.
Sure, sir.
Up and down.
So can we start?
Yes.
So sir, you will be taking up, right?
Yes, I will be doing the introduction and then handing it over to
Yeah.
Mr.
Okay, sir. Okay. Please just go ahead, sir.
Are we online? Good afternoon, everyone. My name is Venkata Simhadri. I'm the MD and CEO of CMOS Chip Technology. I welcome you all today to the interesting webinar we are hosting. So just to give you a brief background, these webinars are hosted by IESAs, and ESA stands for Indian Electronics and Semiconductor Association. We are a premier industry body. We work very closely with central government and the state governments, and also with the industry to help formulate policies to enable the growth of the industry in India. So as part of this organization, we have created multiple focus areas. We call them six. And one of the areas is definitely, semiconductor manufacturing. So it has become a very important topic and focus areas, not just in India, across the world. US government passed a bill approving $55+ billion budget. Similarly, Indian government passed a bill last year. They called it Semiconductor Mission, and they set aside a budget of $10 billion to enable semiconductor industry in India, especially on the manufacturing side. So when I say manufacturing, it includes semiconductor fabs, OSATs, and compound semiconductor fabs. So and also the associated industries, the whole supply chain and ecosystem. So it's become a very important topic across the world, including India. And so if you look at most of the semiconductor industry in India, it's mostly design houses focused, owned by the multinationals from US and other parts of the world, and some local design houses. But there's not much manufacturing happening in India today. And so with this initiative, we are hoping that the manufacturing will pick up. So we need to start creating both design talent, awareness, and workforce to enable the semiconductor industry in India. That is one of the motivations and reasons we are hosting these webinars, so that we can educate and enable the growth of the design talent in India. I mean the workforce. So with that, I'd like to give a brief introduction to Mr. Jattana, who has been working for Semiconductor Complex Limited. Most of you may not know that India does have a fab. It's almost 15 plus 20, almost 40+ years old fab. It's a completely functional working fab, even though it is doing some older technologies, but the fundamentals are the same. I mean, they are doing wafer processing, creating chips that are in production. So Mr. Harpreet Singh Jattana has been working with SCL, and he has worked in key areas of VLSI product design and manufacturing. He was leading a team of 80 scientists at SCL. It is the only foundry, CMOS foundry, as I said. And it has a few processes. It has an FDSOI process. It has a bipolar process. And I think most recently they acquired the 180 nanometer process from Tower Jazz, and probably that's the most advanced process they have right now. But Jattana ji will confirm that. So he superannuated as scientist Z and group director from SCL last year. And he is definitely one of the subject matter experts in this field in India. And we are very fortunate and glad that he has agreed to do this webinar for us today. With that, I hand it over to Mr. Jattana ji, and he will take over from here. Thank you, sir.
Thank you, Dr. Venkata ji, for giving me an opportunity to interact with the participants. So as Venkata sir has emphasized the importance of semiconductor manufacturing in India. In fact, it has been proven that no country can be a economic superpower or even a military superpower without having a good know-how of this particular semiconductor technology. And it has been over the last few years, it has been found that at least having semiconductor manufacturing bases in a country contributes to at least 1 or 2% increase in the country's GDP. So it is a very important part of the industrial growth, economic growth of any nation. And because it has a high efficacy to all other industries, as you are aware, the chip is everywhere, starting from the greeting cards to rockets and Rafales and other such things. So now the government of India has taken a very good initiative. They brought out a semiconductor policy last year to encourage semiconductor manufacturing, CMOS fabs, compound semiconductor fabs, display fabs. We have good strengths in design, but the question is that we don't have any good IP, and we want a Indian company run by Indians and having a stature of like a Broadcom or a Qualcomm kind of that. So we are able to make not only the chips, but the product which is sellable in the market. So unless those things happen, so our dream of having a good semiconductor ecosystem will remain like that. So I will start with my presentations. I will share the screen, and I hope the screen is visible, please. Let me open the, I think the first webinar was held regarding clean room, and which is one of the very key features of any semiconductor fab. And not only the clean room, but cleaning of wafers, cleaning of tools and all those things, which have been discussed in the first seminar. And please confirm if the screen is okay. Is it visible?
Yes, sir, it's visible.
Yeah, okay, madam. Okay, that's good. So it will have three components. First is the manufacturing ecosystem. What are the various segments? What are the various pillars of the semiconductor manufacturing? I will talk brief 15-20 minutes. Then more about the CMOS fabrication process, close to an hour on that. What are the various steps? We will go through it. And then some 15-20 minutes about the Indian scenario pertaining to what's happening and what can happen. My views, or then question and answer. You please feel free to ask any questions. So you see, the industry is a highly segmented industry. So there are various segments, what we call as an ecosystem. As you can see here, there is a process technology where we design the basically components, active and passive components. There can be a number of transistors. There can be a complete passive component suite. and then we design those, and we design on CAD tools first, when then not only the component design, but how to process those, the process design for fabrication of those components in an integrated process flow. So that is a R&D process, R&D part, or a process technology, whatever name you call it. Design, all of you are aware, it's a very important aspect, and the designers will take those components as the designer is just integrate those components. They don't design, IC designers, they don't design the components. They will take those components which have been already designed by the process technologies, and they will use to make circuits, bigger circuits. So that is the design part. And the manufacturing guy, the fab, they will basically fabricate those designs. So they are main, these three, and they are integrated, and how they are linked, the bridge is what we call it a PDK, process design kit, which gives all the information. How the component is designed, what are the various processes, a IC designer need not know that. So whatever relevant information which is required for an IC designer, that is shared by the process technologist. Then comes fab is a factory, as you know, and you see, to run the factory, there are more than 300 types of chemicals, gases. We will see, I will show you some of those things. And not only those gases, chemicals, electric power, vacuum, compressed air, and all those things. Then they form the utility parts, facilities part. So you have to run those. And some of the gases like nitrogen, hydrogen, oxygen, they are called bulk gases. They are required in very huge quantity. So you need to have a plant there itself, close to the fab. Like in a hospital, you have a oxygen plant close to a big hospital. So in the same way, the bulk gases, they are because consumed in a very high volume. So there are few plants inside close to the fab. So that also to manage those things is a big thing. And then finally, out of the many of these gases, chemicals, they are basically poisonous, hazardous, and like phosphine, arsine, we will see how to dispose. And waste management is also very, very important. Then finally, once you set up any factory, there has to be a quality assurance, the product, the life of the product, life of an IC, whatever you are manufacturing, it has to be minimum some 15, 20 years. And you have to ensure that, so reliability and failure analysis and all those, that QA and FA also is a very important part. Then there are a lot of post-fab operations. Post-fab operations, first is the wafer sorting, then packaging. A lot of innovations is going on in the packaging. Starting from 2D to 2.5D, we were doing at SCL now, but there is a 3D, there's a vertical integration too. 2.5D is a horizontal integration, but now 3D. And a lot of innovations in the packaging nowadays. And this also is becoming a part of the foundry, because we have to design interposers and which are being done in a foundry. So packaging also is a very, very important segment of this particular whole semiconductor manufacturing. And so post fab operations, they consider this. And finally, reliability and the quality assurance, and telling the quality, how much life it is, and all those things, making a product qualified for particularly for any like industrial applications, automobile applications. There are rules, there are standards your product has to meet. Similarly, for military and space, there are standards, radiation hardened standards like you have to meet. So that is another segment. And for all these things, you need highly specialized manpower, which is basically having good expertise, trained in a particular process. And then finally, your product should have a market. You should have a market, niche market. And running this whole thing, you see, one is the process, one is the fab they are running, but the entire running of this also, it's making very good yields, 90%, 95% above yields. That also itself is a technology. In one of the slides, I will show you what Micron is doing and how they are doing, and we will discuss. So this is the complete gamut of what we can say, what we call it a semiconductor ecosystem. And presently, we don't have much, as you are aware. If we talk about the industrial scene, we are doing, there may be around a few thousands of VLSI design engineers in Bangalore, Hyderabad. SCL is the only foundry, as Dr. Venkata ji informed. And but it's not industrial fab. We have a capacity of 1,000 wafers per month, maximum capacity 1,000 wafer starts per month. But as you know, the fabs like TSMC, they will be doing more than this per day. Even their capacities of one unit is 40,000, 60,000 wafer starts per month, and there are number of units like this. So it's a huge volume. We are doing very small. It's a single line of equipment. So we are doing it in a very low scale. And though we have the complete, you can say the setup, test packaging, QA, FA, and all those things are there, but it has to be multiplied to a very high volume, and that is the required. So I will just take a few slides, which I will tell some important things about these particular segments. Like when we talk of a process technology, what is the node? Like as we are, government has opened this, they have come out with a semiconductor policy, and people are trying to set up a new fab, a commercial fab. So then the questions arise at what node, and if okay, we have decided the node, maybe it's a 24 or a 45 nanometer. Then 45 nanometer, there are various flavors in terms of voltage, in terms of devices, in terms of you can say the wafer type, in terms of what type of passive component they are giving. So there are different process flavors, and you cannot have start with all these. You have to choose what type of flavors it's to begin with, and later on add certain other flavors. Then the naturally the equipment, and what sort of equipment. In fact, if we see in each of these, maybe a litho or an ion implanter or a CVD or a PVD or an etching, there are not more than 2 or 3 companies, and specifically in there like EUV, there is only one, ESML. So there are 2 or 3 companies, in each of these, and there is a single batch processing, there is a batch processing, and equipment, and so you don't have much choice as far as the equipments are concerned. Only 1 or 2 options are there. So, but you have to integrate those equipments to make a complete line. Then the maintenance of these, because these are very sophisticated equipment, and you have to maintain this, and even the preventive and breakdown, both things, you have to ensure overall uptime of equipment. You see any, even if you see a 90 nanometer process, it will have around close to 600, 700 steps. And if there is a problem in each step has to be done, each step has to be good, 100%. So even if there are 2 steps which are bad, your end result, your end yield will be affected. And similarly, if to process these steps, there might be around 60 tools. If all the tools should be up, and then only you will get a good overall uptime. And then the process has to be stable, process stability, because these equipments, sometimes they drift. Like if I have to, now the geometries are so small, the films which we are trying to grow, they are so thin, like 10 angstrom, and there is a margin can be only 1% or 2%. So if it is more than this, due to some reason, maybe due to your equipment drifting or things like that, so this means your process will get affected. So you have to maintain, you have to make sure that all these things are within those window, within a very tight window. It's a very tight spec. Yield is very important, and unless fab doesn't, if all your batches are not 90-95% kind of yield, you end up losing money. Wafer yield, product yield is also a very important, and a lot of importance is given. It needs a lot of trained manpower to figure out the failure analysis, what is causing the yield loss and how to improve. Turnover time is very important. As you know, when we start the wafer, and within how much time it comes, it indirect way, it reflects yield also. So normally the standard fabs, they are taking 1.5 day per mask, and if there are 60 or between, there can be anything between 35 to 60 masks, and 1 day to 1.5 day per mask. So it has, batch has to come within 2 to 3 months, and turnover time is also important. So these are some of the things, and once the process is developed, it is a integrated flow. So how the process is developed, a brief about that. You see, as I told, there are many steps in the process. When you are developing the process, you will develop some unit processes first. Like in case of even a 90 nanometer, there may be around 200 unit processes. So what do we mean by unit processes? Unit processes means like if I have to grow a oxide, say 1000 angstrom. So I have to make perfect growing of 1000 angstrom oxide. If whatever it's maybe a dry oxidation or a wet oxidation. So this means your process, your recipe, what is the pressure, what is the temperature, what is the gas flow rate, how much time. So all these things you have to fix, and you have to do a number of times. Similarly, the etching, if you have to etch a silicon nitride and how much time you are giving, what is the etchant, if it's a fluorine chemistry or a chlorine chemistry, what is the flow rate, how your the reactants after the reaction, how they're taken out, and what is the pressure, and all these things matter. They become a recipe for that. So similarly, in a process, they are split up in small unit processes, and you make the perfection of those unit processes by making like contacts. I will make 10,000 contacts and I will measure the contact resistance. The contact resistance should be 2 ohms. So I have made 10,000, 20,000 contacts and I have seen what is the variation. Okay, it's close to 2 ohm with the 2 sigma, 3 sigma within that range. So that particular unit process you have perfected. And then finally, then all these unit processes you have to integrate. That is the process integration. They will run in a continuous manner so that a transistor is fabricated or a resistor capacitor. With that, they are fabricated, they are processed in that. So that is how you, and their thermal budgeting is all those things. They are important in that because like I will give one example. Like in our fab in SCL, we had a 180 nanometer. We have different type of transistors, but we have a 1.8 volt. We there are in 1.8 volt CMOS also, NMOS, PMOS. There are two types of transistor: a normal VT and a high VT. Then there is a native transistor also. So it becomes three types of transistor in that. Then we have a 3.3 volt NMOS and PMOS. We have a 5 volt NMOS and PMOS. But you cannot choose all the three in one circuit. You can choose only 1.8 volt and 3.3 volt, 1.8 volt and 5 volt in our process. But there are certain processes of EMS where your design can have all three. And this is because of the thermal budgeting, how, because VT, how you are adjusting the VT and what is your process sequence, how you have integrated those processes, it is because of that. And then there is a BGT also. Then there can be some LDMOS 20 volt, 40 volt. So 40 volt, if you can have with 1.8 and 3.3 volt. So these kind of decisions are done in the process kind of when you integrate the various processes. Now maintaining clean room, we already have one lecture. It's very important. Class 1, maintaining a class 1 clean room is very important throughout the year, whether there is a process going on or not. That is not important. So there are very tough conditions on temperature, pressure, humidity. And there are ways how to maintain the laminar flow, how to maintain these class 1, class 10, and then uninterrupted supply of gases and chemicals. Gases and chemicals will be stored somewhere else, but they will come through the pipes and they will come to the equipment. That pipes also should not generate any, because the ppm, the purity level are not in ppm, they are parts per billion kind of thing. And any small particle, any small impurity can contaminate and it can affect your yield also. Manpower, I told you, it requires a very dedicated, trained manpower for semiconductor manufacturing. Like we had people who can handle these gases, like poisonous gases, phosphine, xylene. The cylinders are kept in a gas bunkers. Everybody cannot touch. If you have to change the cylinder, there is a procedure, and there are people trained for that. They only can do that because it's a highly poisonous things you are dealing with. So some of the equipments are highly sophisticated. So people go for long trainings, how to handle those equipments, how to operate those equipments, how to do maintenance on those equipments. And finally, this operation has to run all days, 24 into 365. for any commercial making for any commercial viabilities. So these are some of the related things. And lithography, I will just spend 2 minutes because it's very important. It's at the heart of a CMOS fabrication. Not that the other steps are not important. As I told, any step, if there is a problem, then you will not get yield. But why litho is important? Because each step, it passes through litho. It defines the structure. It defines the geometry. So at each step, litho is coming. So we started, when we started HCL in 80, we had a 4-inch wafer and we had a G line, 436 nanometer. It was a mercury lamp. And but nowadays, as you can see, from G line to H line to I line, then in 1985s we got lasers, 248 krypton fluoride lasers and 248 nanometer argon fluoride 193 nanometer. These were quite widely used. In fact, 193 nanometer laser were used for 45 printing, 45 nanometer geometries also, even at 24 nanometer. These argon fluoride lasers have been used. What we call it a DUV, deep ultraviolet. And EUV now, one company has made that is around 13 nanometer kind of wavelength, and ASML, and they have given supplied 2-3 I think 2 or 3 equipment to TSMC and 1 or 2 to Intel. Cost of these equipment, litho tool, EUV is close to 250 to 300 millions, but DUV cost 1/10 or even less than that. So it's a very expensive tools, and you can see here it's basically the DUV, which was around 193 nanometer. DUV 193 nanometer lithography have been used for printing geometries which are much lower than 193. In fact, at 32 and 24, even at 20 nanometer, the same DUV, but with innovations in litho. And those innovations are in terms of, you can see, in terms of mask, in terms of illumination modes, in terms of masking OPCs like optical proximity corrections and red resolution enhancement techniques, and all those things are done. Multiple patterning, and the same tool was used for printing very, very low geometries. And now, of course, we have EUVs and things like that. You see, once we put up a new fab, like in India, any company, they will put up a fab, they will first make the building, then the clean room, then they will install the equipment, and finally they will qualify. First of all, each equipment is qualified and as per its specifications, and then your batch processing will start. And finally, when the batch comes, you have to qualify the technology. How do we qualify the technology? So there are standard are available if you in IEEE, and certain fab standards are there. And normally SRAM and voltage references are used. There are many different types of test structures which are used, and those test structures, they are fabricated, they are tested for electro migration, they are tested for NBTI, for high current injection, and TDB, time delay dependent breakdown. So all these the crucial parameters of the technology. So these special structures are designed which can evaluate these particular parameters. How good is your oxide, your electro migration, your metal lines, how much current at various temperature they are willing to, they are able to take. And with SRAM, you can pack very densely few transistors, so you can see the reliability of that device, and of course the voltage references, which can tell you about the stability of the VTs, how your VTs are varying across the various across the wafers, and from one wafer to another wafer in a batch, from one batch to another batch. So there are ways how to verify this particular, how to qualify a particular technology. So repeatability is must. So you have to process a number of wafers, so take these test structures, measure the parameters on 1,000, 10,000 of these, and show that these are within a particular window. And some of these structures are very, as I told, SRAM voltage references, they are normally used. Even in a running fab, there is a, like we will run certain batches once in a month or once in a week, which will be SRAM, which will tell the health of the fab along with the other product batches, just to know about the health of the fab. And even also there are SLM, which we call it a subscribe line monitor, or a PCM, which is a process control monitor. There are basically test structures, like different type of transistors we can put. We can put few contacts and make a chain. So different type of transistor, we can measure the VT across the different, in a wafer, like a 12-inch wafer. From a different areas of the 12-inch wafer, we will put all these structures, and we will pick, and we will pick these structures at different areas and measure your breakdown voltage, your VT, your contact resistance. That will tell you about the health of the wafer and the health of the whatever batch, whether it is within that window or not. So first is electrical parameters or process control monitor or subscribe line monitor, SLM, like we have a subscribe line 100 micron, and there we can put a lot of these test structures which will tell about the health of that batch which has been processed. And there are close to 70 or 80 different parameters which are breakdown voltages of different structures, which are contact resistances and things like that. Whenever a new fab is put, you see, in the initial thing, there will be failures. Definitely it cannot be 90% or even 80%, and there will be failures. The failures can be random or there can be systematic failures. But in the initial stages, if you see, there are chances that more are systematic failures. But as your time progresses, as you can see in this graph, as our time progresses, the systematic yield will start increasing. So systematic yield, this means systematic failures will start reducing. The process is getting aligned. You are having a control of the process. Process is getting stabilized. So your systematic failures will decrease. Systematic yield will increase. And finally, there will be some random failures. There may be some defects. Some particles are sitting because the clean room is not correct. There was some issue in some chamber. So because of that, some particle is sitting and it's affecting the yield. That's a random kind of thing. So the systematic yield will always be more than random yield in a high volume production. So when your process is stabilized, initially you will find a lot of things, and it's very difficult to, a systematic failure is easy to decode, easy to do the analysis of that. But in case of a random failure, it requires certain more amount of work to reduce that. It may be random failures may be due to equipment, due to environment, due to manpower. There can be various reasons for that. But systematic failures, maybe there is something related to the design, something related to the process, something is not matching, or there is some option, some feature in the machine, in the equipment, which is not which is not working smoothly, things like that. So this is also a yield improvement cycle. So when a new fab is set up, it is a few batches are run to basically stabilize the process. Once the process is stabilized, then you have to qualify the process. There are certain batches, there are certain test structures which are made, and in fact 1 or 2 products can be chosen, which are run 3-4 batches. One batch maybe of 25 wafers or more, and you have to see the consistency of the various parameters of those products or the process parameters. And finally, then you ramp up the yield. And the yield normally, as very good fabs like TSMC, they are quoting more than 90-95% of yields. So these are some of the way how we do it. I will just skip some of these things. And running the foundry again is a big challenge, because you have to maintain your class 1 clean room around a year. Very stringent specifications on various environmental, like your temperature, particle count, etc., pressure. Lot of chemical gases you have to manage. They are ultra pure. They are inflammable, some of these materials, silane, for example. So you have to handle those kind of things. Your procurement cycle, because finally these chemicals, gases, they are not manufactured. We have to get it from US or from Europe, and they have a shelf life of 6 months. Some of these have more, but some of these have 6 months shelf life only. So you have to, your procurement cycle, how much you can store within your compound, because these are all hazardous materials. So that you have to work it out. And after those cylinder, what you do, how to dispose the empty cylinder, that also is a big issue. You have to neutralize the cylinder and how to dispose. So there is a big thing. So all these things is specific type of people, trained people can only handle. Then power supply, it has to be very, very neat power supply, which is not like you can say not easily available in India. So we had a lot of transformers, 1 or 2 transformer dedicated for each equipment to smoothing of these. And there cannot be any power failures. So there is something which is known as a DROOPS, which is a diesel rotatory UPS. Because normal battery operated UPS cannot be at a 2 megawatt and 6 megawatt kind of thing. So what we have a DROOPS, it's a diesel rotatory. And this means there is a AC generator and then there is an AC motor. So that is always running. And there's a big flywheel. And once the AC supply is cut, the flywheel has sufficient energy to rotate that AC generator, and it will give that power for close to 1 minute or so. In that time, your diesel generator will be on and it will supply the power to furnaces which require huge amount of power. So these are the kind of, you can say, requirements. There are very, very tough requirements of these utilities. Similarly, DI water, the DI water, it has to run throughout the fab always. It cannot be stable, it cannot be static, and it has to be running at a particular velocity in the pipes, because if the water is running slow, then there can be algae, there can be bacteria in that which can spoil the whole system. So all these things, they are very tough. And to maintain the particularly utilities part, it's basically a, you can say, lot of efforts are required, and there are a lot of dedicated manpower, each specializing in its own way. And then the fab interface to design, I will not talk because I think most of you are design engineers. You know, the EDA foundry has to provide EDA support. And whatever PDK, if there is a drift in the equipment, you have to set the equipment. You cannot change your model parameters every now and then. And but finally, after a few months, you have to releases of different PDK are given. And if there are some changes in the PDK or in the model parameters or in the layout kind of thing that has been, so PDK have to be updated. There are good amount of people who are involved in all these things, particularly when a new process is made. Like you have made a new process and finally you have given a new device, then that device, you have to characterize that device, you have to make models of that device, and the data has to be huge for that. And similarly, when we did a silicon on insulator, SOI CMOS, so you have to have at least 50,000 or some close to a 1 million kind of a data for that to model, to make a, you can see a spice parameter from that, which can be used in a particular help in a design. So there is a lot of work involved in design characterization and modeling, because it involves huge amount of data, and that data you can only generate once your process is stabilized. It is in a particular window, then you have to process a lot of wafers to be able to generate that kind of data. Now I will go to the main thing, which is the sequencing part, and I will just go through the various steps quickly, and we open that. Some of these short, long length I will, you see, in a process, broadly speaking, as you can see that, what can be the different modules? There can be a well, and because well is separate for N and P, and there will be the isolation between the well, and of course there are different types of well nowadays. Super retrograde wells are used. Then we have a gate, and then we have a source drain, and then we have contact of the transistors, and then we have the interconnects, and finally the pad. So these are the various modules, and in any geometry, basically the modules remain the same. And the first process while doing this is we have to make field areas, field and active areas. Active are the areas where the transistor will be fabricated, and the other area where the transistor is not fabricated, that is a field area, or you can say it's a basically a isolation. And nowadays, as you know, that a trench isolation is used, a shallow trench is uh, built inside the wafer, and that is the first step in any process, because it's a very rough step. And how do we do that? First, we will grow, like I will take a wafer here, and again, there are different types of wafers. I will just like to show you some wafer here. If you are able to see, this is a wafer, single wafer carrier. And if, I don't know if you are able to see or not. And this is wafer can be of different type. This wafer is 8-inch, and this is a bulk wafer. There can be epi wafer, there can be soy wafer, and there are reasons for different types of wafers and where each wafer is used. There are around 3-page specifications for each wafer, and for the time being, our concern is the resistivity of the wafer, which is the doping level. Normally 0.5 to 3 ohm per meter if per mm is used. Normally you can see this is a polished wafer. The first, the front side, back side is not polished. So, and there is, you will not be able to see here, there is a small cut here for identification of the wafer, for alignment. Whenever the machine, it goes in any tool, so this particular machine will align. So this is basically the a wafer, and this is a single carrier, and this is a wafer which is a process wafer. Of course, you will not be able to see the various here the reticles, and there are close to 26 designs in one reticle, and there will be total 58 kind of reticles in this. And these wafers, when they go in a fab, they are basically this type of a box. And if I open this box one batch will have 25 wafers, and this box normally the wafers will be kept like this. If you are able to see, I don't know how much clarity is this, and but this box is vacuum sealed. This box equipment will take inside this box, and through robotic arm they will take one wafer, process. After processing, this wafer will be kept at its slot, and then next wafer will be taken. So like this it happens. So now the first is we start with a wafer. We have chosen the wafer, and it depends on when you design a process, you see what should be the specifications of a wafer. And the thickness of the wafer, if you see 12-inch wafers are normally used. They are close to 800 micron. We were using a 8-inch 725 micron thick. And you see, this is the thickness of the wafer, and processing is done only at the top in the polished, and the transistor will be just in the 2-3 micron top surface is useful. Rest is because you have to handle a very thin wafer you cannot handle, and the wafer has to see temperatures like 1000 degree, 1100 degree centigrade. So to give a good mechanical strength, so this much kind of a thickness is kept. Flatness of the wafer, resistivity of the wafer. So we are using resistivity 1 to 50 ohm centimeter wafers, and there are certain epi wafer also, n on n and n on n plus plus. They have their own advantages. But this wafer, normally fab get this wafers. They don't make these wafers. The fab will take unprocessed wafers. And there is a very complex process of making these wafers, CJET and float zone and these kind of thing, which you might be aware of these. But these wafer have to be the top surface, the top 2-3 micron area has to be very, very pure. It should not have any impurity. Rest of the, there can be some impurity, some oxygen, some basically carbon atom, some oxygen, 10 raised to the power 11 per centimeter cube might be there in the lower thing. But in the top, it has to be absolutely crystalline, 100, no impurity at all. Otherwise, it will affect your processing, it will affect your yield. Because processing steps like etching and thin film deposition and growth of a like oxidation, they are dependent on the crystal orientation plane also. So in a CMOS, as you are aware, we are using 100 orientation wafers. So we took the wafer and the first, this is the wafer we have taken, and 1.0 ohm, 1.5 ohm centimeter resistivity. It's an 8-inch, it's an argon annealed, it's a boron doped. Boron doped means P sub. Again, you can have P sub, you can have N sub. There are positive and negatives both of these things, but 80% of the time, normally a boron doped wafer, a piece of wafers are used. And the first step will be to make to define the areas which are active areas where we will make the transistors. Other areas will be the trench. We will make the trench. So finally, we call it a STI, shallow trench isolation, to define isolation areas. So we will grow an oxide. Growing oxide is very easy. It's basically a dry oxidation step. The oxide thickness, again, it depends on the process. If you have process design, it's very small. Say it can be around 200 angstrom kind of thing. So there is this layer. On top of this layer, I will deposit nitride. I cannot deposit silicon nitride directly on silicon because of the mismatch of the two films. So this acts as a stress relief layer also between silicon and the silicon nitride. And it becomes a very good interface. So I have deposited silicon nitride also on this. And now we have, and the layer, as you can see, the thickness of silicon nitride is 4 to 5 times that of the base oxide. If it's 100 angstrom, it's 400, 500 angstrom. Silicon nitride layer is deposited. And the way is CVD, chemical vapor deposition. It can be atmospheric, it can be PE, it can be LPCVD. So each of these topic is another, again, a quite like a separate webinar can be held on each of these process steps, how they are done, and how the equipment is designed, what are the critical issues in the process, how it's related to design, how it relates to the physics basically, or the chemistry. So for the time being, so these steps we have done. You see, whenever we do a step, the wafer goes for a, you can say, cleaning. Cleaning, again, it is by acidic cleaning, alkaline cleaning, water cleaning. So there are standard steps, standard procedures, how to clean the wafer, how to dry the wafers. So that we are not covering. Now we will go for a photoresist. We will cover the entire thing photoresist, and we will take the mask, which is a STI mask, which will define the area. Like this area, it will be removed. The PR will be removed, which is in the red color. And this particular means here will be the trench will be formed, and other area which we are protecting by the mask is the active area. As you can see, and I will remove this by etching, and this has to be a reactive ion etching. This cannot be a dry, it cannot be a wet etching. So here I am using a fluorine chemistry to remove the oxide and nitride, and fluorine chemistry is used in a reactive ion etching. And from here also, it's basically cross section of the wafer. So here this is done, and finally now I have to etch the silicon to some extent, and like this, make a trench in the silicon wafer, and that I will use a chlorine chemistry for doing this etching. This also is a, you can say it's a dry etching, reactive ion etching. It's a vertical because it's a trench, and the width and the depth of this are almost of the same dimension. So aspect ratio is close to 1.2 kind of thing. And so this we will make a trench, and then finally we will fill this trench with the oxide, very dense oxide, because it's an isolation. It isolates two. You can see here we will make, we will fabricate P transistor here, we will fabricate N transistor here. So it's an isolation and it's a cross section. You can see it will become a, from the top, if you see, it will be boundary wall across the house. It is like that. So now the next step will be to remove this, the red, which is a photoresist, that its function is over. We can remove by oxygen plasma, that has gone. And now this is the trench in the silicon wafer which we are observing, and then we have to fill it. We cannot fill with a high dense oxide. We will grow by dry oxidation. And this yellow thing you are seeing here, this is, we are growing a liner oxide, 20 nanometer, 20,000 angstrom, 200 angstrom. You can see we are growing here. It will grow here. It will grow here on top of green, because it's silicon nitride. Oxidation cannot take place. Oxidation will take place only where the silicon surface is visible. So here silicon surface is visible. So you can see a liner oxide has come, and this is done in an atmospheric furnace. And there is a recipe for that. Like, you have to grow 20 nanometer, and there is a 200 angstrom. So there is a proper recipe. What kind of, it's a dry oxidation. So what should be the flow rate of oxygen? What should be the temperature? What should be the time? So all these things, what is the pressure? So all these things design that your process. And finally, when it is grown, then we will fill it. We will fill it with an HDP, that high dense oxide. We will fill this. So fill trenches with oxide. And then you can see we have to remove this, and this area we have to protect. This one where the trenches are there, which is a field area, or we have to protect this, and there is a mask for that, which we call it a reverse active area. Because we call it active area where transistors are made, we call it field area where isolation is there. Field area is also known as reverse active area because it's the reverse of that. So we have to protect that. So there is a mask for that where I am protecting that. I am doing operations at the other side, and I will remove the, you can say, the yellow thing. I have removed the oxide from there by way of etching. And finally, I have removed the, by way of etching, I have removed the photoresist from all. And then again, I will remove this oxide. I will do a polish. After doing this, I will do a CMP step, which is a chemical mechanical polishing. There is a chemical mechanical polishing, meaning there will be chemical reaction on top of this surface to make the bond between the various silicon nitride, silicon to nitrogen bonds weak, chemical reaction, and then mechanically I will rub it, polish it. Make the bonds weak, with mechanically I will rub it to remove that. And that is how, because this planarization of the surface is very, very important. The plane on the top of the wafer, plane's surface has to be very, very plain, the top surface. Because optics, your litho is optics. When you define the structures, the focus has to be on the surface, and surface has to be at one level. And we will remove this oxide. And so we have basically what we have found. You can see this yellow thing, that is an oxide we have found. This is how it looks. This is actual picture taken, and you can see this is the this one here. This thing we are filling with the high dense oxide, and this is how it will look like. You can see here, this is how it will look like. So here what we are doing is we are trying to make only the STI, only the trenches. We have tried to make the trenches, shallow trench. We are trying for that. We are marking the area, we are doing the etching, and we are seeing the geometry of all these. They are within that window. So you have to make that step perfect. And what should be the recipe? What should be the process, unit process for that? So that this is a very first step, and you have to make perfection on that. This step, in fact, has around 20 or 30 different steps, as you have seen here. So after this shallow trench isolation is formed, I will remove this sacrificial oxide, and then we will make the wells. Now, Earlier we used to have a diffused well, we have a retrograde well, super steep retrograde wells now they are used. There are separate wells for N, there are separate wells of P. It is the process people who decides first whether we have to make P well or we have to make N well first. That is a parameter in the design of the process. Well, there will be many masks. There may be 6 to 8 different types of masks. And the reason is because you have to do the profile of the well in a particular manner. It cannot be done in a single mask. So there can be high energy mask, there can be punch, and you have to control the punch through, you have to adjust the VT, and all those masks are here. As you can see, there is a punch through mask, there is a VT adjustment mask. And so designing of the well, that is known as a well engineering, that is a very key step in a process design. Different types of equipments are used: medium current ion implanters, high energy implanters, low energy implanters, angular implants are also done. So there are different types of implants. They are done in various steps to design both the P well and N well. Our finally goal is to optimize both the transistor. What I mean is N transistor and P transistor. I want a systematic. A systematic means a similar transistor, a matched transistor. The VT has to be same of both. Say 300 millivolt, 300 minus 0.3 and 0.3, matching transistors. So that will tell how we design our wells. And designing of well is the profile of the implants. And there can be, and to make the exact implants, there has to be sequence of implants. There, and in implants, two things are important: the dose and the energy. What is the energy and what is the dose? So here, as we can see, P well high energy implant 2 into 10 to the power 13 is the dose, and energy is high is 250 keV. So it's a medium current implanter, and like this. So this is a tilted implant, VT adjustment implant. Because why it's tilted? Because there will be an oxide, and on top of beneath the oxide you have to tilt, and in 4 directions you have to like 7-degree tilt. You have to do the tilted to adjust the VT across the channel. So the well design of well is very important, and basically nowadays triple well processes are used, and these doping profiles of the well, they will affect these critical parameters of the transistor. They will affect the GM, they will affect the VT, source drain punch through, junction capacitances. So you have to minimize all those capacitances, carrier mobility, source drain to substrate breakdown voltages, sensitivity to body effects, hot electron effects. So all these things, the well design will be impacted. And again, our target is we have to squeeze it. We have to place. We have to do a very high packing density. So N plus 2 P plus spacing also. We have to reduce the spacing between two wells, and we have to make the well shallow, because deeper well will not be of any use. Rather, it will increase your capacitances. But if we make more shallow wells, then there should not be vertical punch through between the well and the source drain. So then resulting in a very high leakage currents. So all those things, there are many like parameters which a process designer has to deal with in making these well and source drain. Later on, the well engineering and the source drain engineering is very important step in the design of the process. And finally, all these implants are set. They are in a software program. The fab engineer will just select the particular step which is there in a batch card, in the run card. He cannot fiddle with this. He cannot change anything in this. And once a process is frozen, all those parameters are frozen. And fab people, they will blindly run those. They will select a recipe, they will select a process and run it. They are not authorized to change this. And if there is a requirement, it is to be changed after a deep failure analysis and things like that. Then only some changes are done in this. And so this is a diagram. If you see, I will not be able to explain much because of the paucity of time, because each of these things again itself is one lecture. So this is the profiling which I need. Here, this is on the surface. The concentration of doping is less. Concentration increases, I get one peak, then it falls, I get another peak, then it falls, then I get another peak. So I want this kind of, this is super retrograde well. And here it is less because I have to adjust VT, it cannot be more. Here it is more because I have to control the hot carrier injection. Here it is due to vertical punch through. And here it is due to latch up, I have to make it very high. So there is a reason for that. And what is the dimension from this? That also it is in nanometer. So basically point is, these well engineering is a complicated step. In a design, you first do it on a TCAD, then do it on a machine, and finally find this. So this is the one. And I will select, like here, what I am doing is I am here photoresist for P well formation, because where NMOS transistor is there, so P well has to be formed, and this area in the red I am blocking by a photoresist, and I will do the well engineering here. As you can see the steps, so number of implants will come. Number of implants will come. First, high energy implant will come, and here, as you can see in the red, it will not penetrate inside this area, but here it is there. And then other implants will come, punch through implant, then the VT adjustment implant will come. So all those implants will come. And then finally I will strip this. This P well is formed. In the same way, I will form the N well. A number of implants will come, and I will form the wells. So you can see the color, and there is a P well, there is a N well, different wells are formed, and now we have to form the gate. So now after these wells are formed, annealing is done, and there is a rapid thermal process also. Basically, you see, when we do the implant, if this is the surface, I am doing an implant here, the boron will sit just below the surface. It will not form, it will not go deep inside the crystalline structure. And for that, there is a anneal step or drive-in step, which is at a high temperature. For some, say 20 minutes, 30 minutes at some 800 degrees centigrade or like that, then you get a proper profiling. Then you get a proper profile. And while doing the implant, the top surface of the wafer, because implant basically is a collision. There are boron atoms which are striking, phosphorus or arsenic atoms which are directly hitting the surface of the silicon. And silicon is a crystalline structure, so it distorts the surface. And annealing, again, some of the crystalline structure which is distorted, by annealing it regains that. And because in the well I have to make a gate, and on the gate, as you know, where I will deposit the silicon oxide to make a gate, below this will be the channel, and that area has to be very, very neat and clean, crystalline structure. Otherwise, it will add to noise. It will add to more leakages. So all these steps are done in this particular manner. And finally, the gate oxidation and poly. And gate is normally okay. We are considering an oxide, or it can be a nitrated. There can be, you can say at 65 nanometer, there is a this silicon oxide or a nitrate cannot be used at a gate. There is a hafnium oxide, but hafnium cannot be deposited directly on the silicon. There is a small thin oxide layer, then hafnium, then oxide layer, and then your poly on top of it. So the gate module is also a very critical module. There are a number of steps involved in this, but each of these modules require 1 or 2 lectures. And that's why I'm going through it, telling the critical points of each, but I will not be able to explain this. And you can see here, nitrated oxides are useful because of so much reasons, and things people have struggled for high K dielectric. Various hafnium oxide is used, aluminium, silicon, and all those things. These are the various material, and how decide based on the energy band and work function kind of. This is the basically physics. I will skip some of these. So gate oxide, which is a very critical step, it has to be clean. It is done a number of times. And how much oxide has to be grown? When a process designer designs a process, he has to keep in mind in this process, like I will have 3 transistors, 1.8, 3.3, 5. 1.8 volt transistor will have a gate oxide of say 30 angstrom. 3.3 volt transistor will have a gate oxide of 70 angstrom. 5-volt transistor will have a gate oxide of 120 angstrom. So how I have to do this? And that is the thermal budgeting of that steps. So how, because all these things I have to make a integrated process flow where these oxides of each are done within the same thermal budget. Thermal budget is taking the wafer at a particular temperature, because a high temperature which affects the, you can say, distribution of these below atoms lower where VT is there. So that implants atom can disturb at a high temperature. So here, after the oxide, we will do a polycrystalline. We will deposit poly by using CVD. And again, we will define the gate length here based on the photoresist. And this is the photoresist. It will look like this. This is the gate oxide. On top of it, we have deposited the poly. And both sides, it can. Now with the metal gate, let me. Then finally, you see now here, this is okay. When we are doing a till 130, 95, 65, we are doing only the, we are changing the dielectric, and gates are definitely P plus and N plus. They are polycrystalline gates, but they are not metal gates. At 45, the whole thing, because of the reasons which we cannot divulge here, the gates will change, the metal gates will come. And then the metal has to be different both, for P different, for N different, depending on the work function which suits that particular P transistor and for that N transistor. So there are two processes in that. One is a fusee and another is we cannot deposit the metal right now, because after that the source drain are formed. You see here, source drain are not formed. We are making the gate first. And for source drain involves high voltages, high temperatures beyond 700 degree or so. So if I use the aluminium, I cannot use aluminium as a gate, because after that there are steps where I have to take the wafers to 800 degree, and aluminium cannot go beyond 520, 550. So in case of metal gates, normally what is done is, first we will stick with this silicon and we will do the source drain, and after that the gate, silicon gate is removed, and N side, P side, and filled with the appropriate metal on the N side and P side after source and drain. So all these steps are done in case of HKMG kind of thing. And how to choose the material, that is again we will not see here. And there has to be a LDD kind of a structure for a source drain. So for that we have to make a spacer. You can see this thing. This thing is called a spacer, because here I will have a low. Here I will have a lightly doped, and here I will have a more, because you see any junction where there is an abrupt change, and the electric field will be across that small area, and we don't want a abrupt change from source drain from the channel side to the source drain. I don't want any abrupt change. So I want a lightly drained, lightly doped drained area. So as if I try to explain here, this is the gate, this is the channel. Channel is you can say P, and here is the N, here is the source drain. So here I have N plus, so this area means it is lightly doped, and this area is N plus, and it is highly doped. Why can't I have the entire N minus? Because I have to make contact here, and the contact resistance will increase, and I have to decrease the contact resistance here. I want more of N plus plus here, and here I cannot have an abrupt junction. So I have made an area. I want to make this source drain like this. In this area, it has to be a low concentration, lowly doped, lightly doped, and that I should have a stopper on top of it. So the stopper is of silicon nitride, and so these are various steps of doing this source drain formation at one transistor and at the second transistor. So both these will be done, and there are a number of steps in this, and finally we will make the source drain, and finally these transistors are ready, and we will make the contacts. And you can see this is the spacer, this is the gate, this is the gate, and this is the spacer, and here it will be a lightly doped area. So these spacer, and that is the reason you see this particular structure, planar structure, There will be one transistor here as shown here. Now, if you see at below 24 nanometer, why we cannot do this? Then your FinFET starts. The reason is you have two gate. This is one gate. This is another gate. How close these two gate can be? What is the minimum dimension? You need one spacer. You need one spacer here. This one spacer, and this one spacer of this transistor also you need. So you can see the geometry of this spacer and geometry of this spacer. It will come. Then you have to make a contact here. Source contact, source drain contact here, source drain contact here. So if you add all these things, so you will not be able to make a transistor usable if you reduce the geometry beyond 24, because you cannot have a contact of 2 nanometer or spacer of 1 nanometer kind of thing, contact of 2 nanometer here. You cannot shrink the contact very small. Contact resistance will be very high. You have to make a very deep contact. Aspect ratio will be very, very large, and it's not possible to fabricate uniformly. And the contact sizes cannot be reduced to nanometer kind of thing. And that is how here you will not be, it's not possible to shrink this particular structure beyond 20. And that's how the FinFET and DGFET and all those things have come. And FinFET also after 3 generations below 5 nanometer, it's not possible. Then you have a gate all around and all those things, which is the physics of, and there the fabrication steps become entirely different. So we are doing the source drain of both these. We have done the source drain, we have done the contacts, and then contacts on the silicon cannot be, we cannot put directly any, you can say aluminium or things like that. So we have to reduce the contact resistance. So now normally a silicide is used, a cobalt or a titanium silicides. We were using cobalt. So we will put a cobalt here. So on top of, you can see here it's cobalt is put, and then cobalt will react with silicon to make a COSI2, what is known as a cobalt silicide. It's a very thin layer, few nanometer layer of cobalt is put, and then you can see here it's a cobalt silicide will form, and then on top of here also it's a cobalt silicide is formed. So there is a step to even deposit the cobalt layer, then to do the patterning, to remove, to etch the not required cobalt layer, and then finally after that you have to do the other things. 45 nanometer, because in the channel you have to use a strained silicon, because by reducing the channel length we do not get the advantage because your mobility suffers. To increase the mobility we have to strain the area in the where the current flows, where the charge carrier flows basically. So how we done, and that the way is different for NMOS and for a PMOS. And for an NMOS, what we have to do, for a PMOS, in the source drain we have to put a bigger atom, like if in case in silicon germanium is bigger, so you put a germanium so that silicon, that channel area is squeezed, so there is a tensile stress occurring here. And in case of an N, we will put in the channel after the VT we will put some germanium atoms, and so that there is a stress this way, longitudinal stress, so that way it will affect the your mobility, and those things are done. So then after making the contacts we can make tungsten plugs, and then there will be a metal, between two metal there will be a dielectric, and dielectric layer, interconnect layer, then dielectric layer. If there are 4 metal or 5 metal, there can be different dielectric, and it's basically a silicate glass. It's a boron phosphate silicate glass, or some oxide, thick oxide is there, and it depends on what is your thickness of metal layer, then the thickness of your oxide layer. So you keep on doing this, and in case of a copper, nowadays we have a copper beyond below 130, there's a copper, and so there's a you can say a damascene process, and because copper cannot be etched, so that process is entirely different, and you keep on adding these particular metal layers on top of it, each and there. So you can have a different metal layers each on top of it. Like this, it goes on metal 1, metal 2, metal 3, and the last layer will be a very, you can say, a thick metal, which will be there in the top. And if there are 6 or 8 metal, the last layer, and these will be the tungsten again. Then why this cannot be aluminum? Why cannot be this copper? This is because of the processing where aspect ratio is there, how you do the etching, how you deposit the films, how you do the patterning. So all these things depends at what temperature you do. Because here you see that is known as the back end of line. Once the transistors are made, all operations where we are growing metal lines, we are growing your interconnect lines, we are growing your dielectric lines, so that forms the backend operation. They cannot be at a higher temperature. They cannot see processing temperature below 700 and 800 because your profiling will disturb, your implants will disturb here. So they cannot. So this way, it has to be chosen. The material, it has to be chosen so that your processing steps, once the transistor is made, cannot see very high temperatures. Till your it's not ready, they can see high temperatures, but after that they cannot see very high temperatures. So this is one part of, in a very nutshell, in the time given, what could have been. This is what could have been done, and because each step is a very complicated, very interesting step, and a lot of physics, chemistry goes into this, and it's a very interesting even subject also to know. And just again, then as I told you, lot of gases, chemicals are needed. You see here the bulk gases, they are needed in huge quantity: nitrogen, oxygen, hydrogen, argon, helium. So these are some of the quantities we have in nitrogen plant, hydrogen plant. You can see these big cylinders, big, I think, I don't know how many, it's close to some 40-50 meter high. Big cylinders we have a nitrogen plant we are doing, as you can see in this figure. So, and they are distributed gases through special pipes, stainless steel. This is the number. These tubes, they are not made in India. They are all imported materials. And then there, if you see here, the purity levels that are very stringent. And once these things go through these pipes, there are monitors at 2-3 places which checks their purity levels. Once their purity level are disturbed, it will immediately raise alarm and stop the supply. So those things are very, because it can spoil the entire it can contaminate the entire tool, and it will be very difficult to redo that. Water is very important because after each step there is a washing of the wafer, and water means only H2O. There should not be anything. And pure H2O, it has a resistivity of 18.2 megohm centimeter. And these are the parts per billion. You can see 0.550 boron, sodium, this. Continuous supply of so many grams per minute, 450. It has to run through continuous supply of water. Continuous supply, because if the water is static or running at a low speed, there are chances of algae or a bacteria in that, bacteria formation. So it has to continuously flow. That is the reason whenever any people are trying for a fab location, so location has to be where a good amount of good water is available. And we have a water plant which is a very big, lot of processes are done to achieve this kind of a ultra pure deionized water. And so it's need high volume of raw water. Maybe for each 500 liter of water, only 1 liter is made, which is ultra pure, and finally it is circulated continuously, whether your batch is running or not. Water cannot be static, because then the whole network, it will spoil. And other things like all types of acids, alkali bases, solvents, which we studied in 11th and 12th chemistry, they are all used. Hydrochloric acid, hydrofluoric acid, nitric acid, phosphoric, ascorbic, bases, solvents. So all are used in basically today's processing. Implantation, these are the general material: arsine, phosphine, diborane, silanes, silicon tetrachloride, trichlorosilane, dichlorosilane. It's basically for growing of poly. So all these materials are used. and they have to be, there are ways to store this material, how they are transported to the equipment, and after processing, whatever the end products are there, how they are taken, and finally how they are used, and after processing. So these are some of the chemicals which are used in etching. It's basically a fluorine, chlorine. These are the standard depending on your how you have designed your process, and requirements. Huge furnaces. There are furnaces which have to constantly maintain a particular temperature, 1100, 1200 degrees centigrade. So you need a very neat, as I told you, very neat power supply. There should not be any ripple. Neat means there should not be any ripple on 440 volt, 415 volt. So basically, there in a series, 2-3 transformers are required. And UPS is finally, as you can say, 1750 kVA into 3. So it's basically a megawatt kind of power you need. And you need DG sets, diesel generator sets, in case there is a failure. Some of the equipment are so critical, like in a 50 hertz, if the power goes before the zero crossing, the equipment needs power. You can calculate how much millisecond it comes in case of a 50 hertz power line. So that is the reason DG set, it takes 1 minute or 1.5 minutes, 1 to 2 minutes to start. It cannot start immediately. Your battery is okay. Battery UPS which we are using with our computers, that's okay. That starts immediately within microsecond or so. But DG set cannot start. So that is why we have a droops which can give supply only for two minutes. And finally, your DG set will start. And droops is a, as you know, there it's a very big generator. You can see here, these are the pictures. There is a AC machine here, AC generator, AC motor, AC generator. They are coupled by a big, you can say, a flywheel. Now this flywheel is decoupled from the AC generator. Very fast switch. But constant supply is being given to the AC motor. So flywheel is running continuously. So once this power is cut, the motor will stop definitely. But flywheel is continuously rotating. It has some energy. And the switch, it's a fast thyristor kind of a switch, which can be on in microsecond. It is on and flywheel is connected to the AC generator and it will give supply. But this flywheel has only energy for say 2 minutes or 3 minutes. So within that time, it will supply the power, and within 2-3 minutes, your DG sets will take over and they will supply. So this is how it's a big room where these three things are put. If somebody get a chance, I think you should visit SCL. This is at SCL only, and one place or two places at Air Force Station, Air Base, where they want radar and things like to be not to be disturbed, and they had also installed one of these troops machines in some of the air bases. So only at one or two places this kind of facility is there, and you need special people to be able to handle these kind of an equipment. You see, it's a basically, if you have to run a commercial operation, you have to minimize cost. You cannot give your what you call it a your maintenance contract to, because then it's 15-20% of the total cost of the equipment. It becomes too heavy. So what we have been doing at HCL, the first level of maintenance, and our engineers were doing only once in 2 years, 3 years, which we are not able to do. We used to call the OEM. Otherwise, 15-20%, if your line cost say 1 billion and 20% is 200 million every year, you have to pay on just maintaining the equipment. So this is how you have to optimize. But okay, then the TMC, like, they have very huge number of equipments, and the OEM is stationed there itself. So their game is different. So these are some of the other thermal systems. Cooling water, process cooling water is required, dry air is required, vacuum is required, exhaust is required. You can see these big pipes, they are exhaust pipes. So it's basically a big factory. It's not a one factory. Fab is not one factory there. It's basically a cluster of 5-6 factories in one complex that forms this thing. So maintaining the inventory of raw materials, equipment spares, consumables, lot of equipment consumables are there. Every 2 months, 3 months, you have to change. the consumables, and you have to maintain the, and life system is very, very important because we are dealing with the chemicals which are very, very dangerous and toxic gases. And you can see these here, they will raise alarm, and there is a way how to monitor the toxicity and hazardous nature of these. So there is a coaxial tubing, continuous monitoring through any leak code, even a one molecule leaks, it will give an alarm. Because if a quantity, even in a small ml kind of thing, it leaks, it can be very fatal. So there is a life safety systems are very, very important. Then fire systems are very, very important, and waste management is very, very important. And whatever wastes come from the fab, it has to be basically neutralized, make it at pH normal, and then how to dispose. Lot of water is coming. There is a lot of chemical mixed in that. So how to dispose energy, your cylinders, gas cylinders, you have to neutralize and dispose. So these kind of mechanisms are there, how to do it. And now, as I told you, fab is one part. There are other operations like you have to test wafer. This is a wafer prober. Automatically, you have to probe cards, how to test blade type, epoxy, overhead salt, automatic test equipment, over the head toss, FIB, temperature testing, and all those things. They are RF testing. So there are big ATEs. And finally, you have to test the wafer, test the product. And finally, you have to do the packaging part. Nowadays, packaging is, people are talking about 3D packaging, but we have done all the CQFP, PGA, PGA, 2.5D, multi-chip module and things like that. And then finally on device, you have to do all these reliability, like operating tests, thermal shock, bend, mechanical, constant acceleration, all those things. So there are equipments which will do this. And finally, as I told you, its manufacturing is itself a technology. This slide was sent me by a colleague who is working in a Micron. I had a long talk with him. What he says is around 15 years back, when there used to be a rework at our batch, we used to take time, and yield were also okay because we have to maintain 90-95%. But for the last 6-7 years, whatever fab we have, there is no manual entry. There's no person inside the fab. It's all fully automatic. If some alarm is there, then somebody goes and fix that alarm. There's an end-to-end automation of operation. Totally fully operated fabs, fully automated fabs. And lot of IoT is used, lot of AIML techniques are used. Each processing, lot of images are taken. AIML software will capture those images, and they will see if there is any defect in those images. If there is a drift in the equipment, there is an again AIML software and connected to the OEM, which are monitoring that. So there is a huge amount of data which is analyzed. So engineers, lot of engineers who will think what they are sitting outside, they are sitting outside the fab, they are maintaining, they are managing that kind of data. And a huge amount, I think to a very large extent, use of AI to see the wafer imaging. We used to see wafer, our persons used to see wafer under a microscope. Is all patterns are okay. There are any defects in that. There is no device, no particle sitting on the wafer, no scratch on the wafer. Manually, we used to see our person, technician, and sign. But now, lot of AIML in processing, while in the process, because there are 400 process. If at the end of 200 process, there is some portion of the wafer which is bad, so there is no point in taking it further. Either do it for rework. If rework is not possible, discard it. Don't add further processing cost. So that person cannot decide. 20,000, 40,000 wafers you are starting. So that automatic, your metrology tools are very important. In a fab, there are two types of tools, process tools and metro. Metrology tools, they will either measure the electrical parameters, thicknesses of the film, they can vary the composition of the film, and then the geometries if some particle is setting, and the geometry. So all these different images they will take. So at what stage, what is relevant, that is what the process people decide. And this is what he says, and use of these things have resulted in faster time to yield maturity, increase in manufacturing output, quality 35%. So that is how they have improved on the yield, they have reduced the time, and they have improved the reliability of the device by use of these IoT and AIML and all those things in the and fully automated way. At HCL, our line is semi-automated in the sense, these kind of what I showed you, these kind of boxes. So these type of boxes are from one machine to the other machine are kept by the technician. They will take this box, put it there. But they will not open the box. Wafers, I am showing you, it cannot be handled by a bare hand. It cannot be opened. It goes in box, goes inside the machine. It opens it, take the wafer, process, put it back in the wafer. Close the vacuum, seal the box. It comes. Then it goes to the next. So that is a semi-automatic. Fully automatic, everything goes on a conveyor belt. So this is how the latest Intel TSMC fabs are built. But again, then you require 5 billion, 7 billion for that. You not only the money, you require the technology for that, with making all these things. And you have seen it's a lot of things involved in this. It's not just the pure process. It is the manufacturing technology to be able to consistently stabilize, consistently manage around 95% yield. So that is what is required. So with this, I will stop and I will be willing to take questions.
Thank you, Mr. Jattana ji. I think 2 hours is a very lesser time for the topics that you have covered.
Yeah, because each topic is quite specific. There's a lot of things involved in this.
So we had to skip so many slides in between.
Yeah. Because it was not possible. Because one slide, some of these slides needs 10 minutes, 20 minutes each slide. Because if you have to go to the stepwise, actually each module needs one lecture. So that is if we have to understand correctly the entire physics, chemistry, and electronics behind that. So, but anyhow, it's just to give a flavor of what goes in the CMOS processing. I feel it should would have served the purpose. And I think if there are questions, I will be glad to answer.
Audiences, please, you can post all the questions here. While participants post questions, I have one thing to ask. See, when we're talking about the chips, we can't skip talking about the Moore's law. So, in the interest of this latest CMOS technologies and this scaling, so how is it challenging Moore's law?
Yeah, you see, because now TSMC, as you are aware, they have already started 4 nanometer. They have planned for 2 nanometer and 1 nanometer at the most. That they call it a gate all around kind of a thing. And Samsung also beyond 1 nanometer, that gate all around will not also. You cannot scale beyond that. Now, that is why people they are talking of more in the sense it basically had to be more advancement on the packaging side on the because already you see the transistor has been so small. It has been very like 4 nanometer, 5 nanometer. Now there has to be improvement in the architecture from the digital side also. Transistor already has been made so beautiful, and then to keep the Moray running in future, to keep the Moray alive, lot of innovations in the packaging side, like different types like RF if you have to do, it might be useful not to integrate with the CMOS logic, better on a gallium arsenide where you can go up to many beyond 40 gigahertz kind of thing, which will be very difficult on a CMOS. And but then memory you cannot do there, or a analog you cannot do there. But you can if we are able to integrate in a 3D kind of a packaging. So that is how the people are working more on towards the packaging side, where different chips done in different substrates, but how to make the packaging to reduce the time, to reduce the signal flow, to make it more efficient. And that is how it will, I think we will be able to keep the Morella alive in the next 10, 15 years. People are also working on single electron transistor, a lot of fancy stuff are there. And I don't know, quantum dots, transistor dots, and all those things. And when it will be realized, maybe after 10 years, after 15 years. But the point is here, this CMOS process is so cheap. The per unit, per transistor cost, you see, it is not even 1 cent. It's not even 0.1 cent. So even if you see the cost of any processor which are being used by Intel, the latest processor which are done, they are doing in 7 nanometer. The cost may be 20,000, 30,000, but it has 2 billion, 3 billion transistors. So one transistor cost is is negligible almost. So with this, I think the innovation from on the process side, it is already reaching the threshold. And definitely it will keep pushing. People are trying different alternate, like planar structure, FinFET we came, FinFET we had 3 generations. And then finally there is a gate all around, 2 generations of gate all around. After that, something else will come. And this particular structure cannot be some new materials people are working on to 2D kind of thing. Now people were saying in 2D kind of material, if you can synthesize different layers and stack on that, you can achieve some 50 gigahertz, 70 gigahertz kind of very fast transistors kind of thing. But still it's on lab scale. To make it commercially, it will take another 20 years or 25 years. But I think this industry right now, the packaging, as you might have heard, lot of focus on packaging, 3D packaging, and to make the product. Our goal is to make a product, and product needs all. It may have various like digital, analog, sensors integrated in one form. Particularly the MEMS devices, where they send something, and then your processing is our in a chip. If those can be integrated, we can make a smart product. And a lot of innovations in packaging are happening.
Right. So we have got one more question. Says, what is the purpose of chemical mechanical polishing in CMOS
Yeah,
process?
this is the please.
Yeah,
This is
that's
the
the
question.
one.
Okay. Because you
CMOS.
see, chemical mechanical polishing means the wafer surface has to be, when we deposit the high dense oxide, the surface is not planar. It's a curvy kind of thing. So it has to be very plain. It has to be planarized. And the reason is we have an optics, because your patterning litho is basically all light optics, and focus can be only at one plane, because then only the geometries, if the surface is not plane, so the focus on, say you are focusing on this higher side, but there is a slight you can say dump here, so it will be out of focus there. So your geometry, where it's very small, we are printing a 10 nanometer by 20 nanometer polygon, so it will not print by 10 by 20, it may be 12 by 18 or some other. So plane, the surface has to be plane, and the further processing will also affect. Further deposition of film, I am depositing 20 angstrom. So where it's deeper, it will deposit 20 only, and 2 angstrom it has eaten. So on top it will be eating, then also the surface will be rough. So the particularly in the, that's why it's in the initial stage. Well, when we do the trench, that is a very rough, you can say, your process. When we fill this, and even in the oxide, when we put the oxide, sometimes we do the chemical mechanical polishing to planarize that. It's just like filing, just rubbing mechanically to make it, you can say, planar surface. And but if we rub it, there are chances you disturb the areas below that. So we have to make the bonds of the chemical bond. It's a covalent bonding there, weak, by chemically. So that chemically, that material is there by which it can, those bonds are weak. And then there is a brush, there is a chemical, there is a mechanical brush which will scrub through the surface, and it will make it completely uniform. Uniformity can be checked by the equipment. It's then there is a metrology tool which will check the uniformity. It will check if there is any particle sitting on it. Whenever any wafer goes to a tool, on the surface of the tool, it is checked if there is any particle, maybe a small particle sitting on it. So that is verified if it is by taking an image. And after the processing, when it comes out of the tool, then also it is verified if there is any other particle. Maybe the tool is contributing to that contamination. And how that contamination reaches the tool, maybe through the pipe or something, maybe the wall of the tool, the container. So there can be multiple source of that. But finally it is checked, and a lot of inspection steps during the process. So it's a, planarization is very important now at below 100, at even below 200 nanometer. When we were doing 4 micron, 5 micron, it was okay. These step is not there. This CMP starts at 350 nanometer, below 350 nanometer. where it is important. At 1 micron and 2 micron, this chemical mechanical polishing is not there because small disturbance it can take. But now at this geometries to below 200 nanometer, it is not possible. So the surface has to be completely planar.
Sure. In the interest of time, we'll have one more question and then we'll close it. So the question we have is, even the modern processors are, vulnerable, security vulnerabilities are possible, like meltdown and spectre. So how to avoid them? The security vulnerabilities.
You see, in the fab side, if you see the process, whatever GDS you have given, we have printed that, and we are not adding anything on that. Whatever GDS is given to us, we will make the mask. The fab is going to make the mask set based on those masks, based on your processor design. That it will be fabricated. The chip will be fabricated. So I think the fabrication has not much role in that. So whatever the design is, we are fabricating it. We are not adding anything. There, though people say that if I have as a processor design, this is particularly the very DRDO and defense organizations, they are very critical that we don't want to fabricate our design at an external foundry. They will add something, add some circuit on that. Maybe they have developed some expertise adding something, and which when you test, you are not able to identify that portion. But now I think in the testing also you are able to identify if some portion is there which is not responding as per your design, which some additional circuitry has been added or not. So because they can change the mask they are making, the foundry is making. Wow, we are not making. We are giving them the GDS file, a mask they are making, and they can add something onto it. That is possible. But normally, I don't think the companies, the foundries, they will be doing these things. But the defense people, DRDO people, they have a lot of suspicion. That is why they want, like our circuits have to be processed here only. And but design is critical. Whatever you are designing, the foundry is implementing that. And whatever protocol from security point of view you are keeping in that in terms of your firmware or all those things, that is to be taken care at the designer end.
Great. To all the participants, you can send your questions to the email address shared by IESA, and you will be addressed there from the email. And the video recording of the webinar will also be shared. Now I hand over to Venkata Garu to give a vote of thanks.
Thank you, Mustaq. Jattana ji, it's a wonderful webinar. I, did work in a fab during the early part of my career, and
Okay.
and that was at 1 micron IDT fab.
Yeah.
And things have come a long way, and most of the language you're speaking, I mean, it's refreshing my memory, but most of it is still Greek and Latin to me. And it tells me, how much the technology has advanced from 1 micron. I mean, 1 micron to, as you said, it's reaching almost 1 nanometer in a few years. So it's been I mean, it's definitely a tremendous, one fantastic webinar. I hope, many students and many, industry professionals who are aspiring to get into manufacturing, or at least in the design side of things, but don't have much knowledge about of a processing side. It's a good eye-opening webinar for them. And definitely, right, as the manufacturing is taking a lot of focus in India and abroad, there is going to be a lot of employment opportunities as well. And this is one area, I think, some of the Indian, universities worldwide also, people started reinvesting into, processing related courses and developing the manpower. So once again, I like to thank you for really taking I mean, you put your heart into this webinar. The material you prepared is wonderful. I mean, it's fantastic material, and really thank you, with my full heart, and it's a great experience for me to be in this thing as well, in this webinar. And I also like to thank my IESA team, Sharat Kaul, and I don't have all the names here, my admin staff, and especially Mustaq, who spent a lot of time in marketing this webinar on the social media, and helping us getting people signed up for this. I thank all the support staff. Sorry I don't have all the names here, but you put in a good work in making this webinar happen. And we will be conducting more webinars, related to semiconductor manufacturing. Please stay tuned. And with that, I like to end this webinar for today. Thank you so much.
Thank you, sir. Thank you.